Hello everyone, this is going to be your solutions for the homework 7 from chapter 19. Okay, let's look at this. Which of the following aqueous mixtures would be a buffer system? Remember, we talk about a buffer is something that you have the weak acid and the conjugate base of the weak acid, or weak base and the conjugate acid of the weak base. Okay, so you have to choose that looks similar, but if it is a conjugate acid base system, you have to see whether the number of hydrogens are going to be less than your conjugate your acid, and if it is for a base and conjugate acid, you want to see if the number of hydrogens increased of the same species. Okay, so with that in mind, let's see the first one. First one is sulfuric acid, H2SO4, and acetic acid. They both are acids. First one is a strong acid, second one is a weak acid, so they are not going to be your buffer system. And then you have second one, H3PO4, and when a one hydrogen lost, it would be H2PO4 minus. So that looks like it's a conjugate acid base acid and the conjugate base system that would be appropriate for a buffer system. There we have an answer. And then we have nitric acid is a strong acid. Sodium nitrate is the salt that nitric acid would make with a base. So that's not going to be a buffer system. Hydrochloric acid, again a strong one. This is the salt. Ammonia is a weak base. Sodium hydroxide is a strong base. So that's not going to be a buffer system either. Okay, so you understand which one is the buffer system now. Number 2, which if any of the following would be a buffer system. Same way that we did for the first one, you can see if the number of hydrogens going to decrease with the same atoms. H2CO3 1 less, HCO3 minus. That looks like a buffer system. HSO4 minus, HSO3 minus. So what's the difference here? It is the different number of oxygens, but that's not a buffer system, right? Excuse me. H2PO4, HCO3. Excuse me. So this one has 2 hydrogens and 1 hydrogen, but the other atoms are not the same because it's not the same component. Okay. And then the next one, acetic acid and sodium hydrogen phosphate. They are also 2 different components. So they are not conjugate acid-base system. So we understood which one is the correct answer. Number 3, which of the following mixed with equal volume of 0.1 mole aqueous ammonia will produce a buffer solution? Now here ammonia is a base. Okay, so if ammonia is a base, what you need to do is normally base will grab a proton from the medium, could be from water, and going to form ammonium ion. If ammonia are going to make a buffer system, it's the base, its conjugate acid component has to be something that has ammonium ion in it. So then you're going to choose the answer that contain ammonium ion. This is sodium hydroxide, not the correct one, not the correct one, not the correct one, not the correct one. And ammonium chloride, the last one, you have ammonium component in it. So that looks like the buffer system. Okay, ammonia with ammonium chloride will make a buffer solution. Number 4, which of the following pairs of 0.1 molar solution when mixed will produce a buffer solution? Again, you have to look for the conjugate acid and the base. Acetic acid, sodium hydroxide, not that one. As sodium acetate, sodium hydroxide. They are also not your conjugate acid-base pair. Acetic acid and hydrochloric acid, both are acids, one weak, one strong. Sodium hydroxide, hydrochloric acid, strong acid and strong base. Acetic acid and sodium acetate, there you go. That looks like your buffer system. Okay. Number 5, which of the following has the highest buffer capacity? Remember, we talk about the highest buffer capacity would be if they have a concentration higher of the both components, and another criteria would be they are concentration should be close to each other. So with that in mind, let's see which one is the highest buffer capacity. So 0.5 H2PO4, 0.5 HPO4 2 minus. That's 0.5. And then 0.1 H2PO4 minus 0.5 HPO4. So one is 0.1, the other one 0.5. 0.5, 0.1, 0.1, 0.1. So B and C, their concentrations are not close to each other, so they are out. And then the A and D, one is 0.5, the other one is 0.1 for both. So we choose the one that has the highest buffer capacity. So which one is bigger, 0.5 or 0.1? 0.5 is bigger, right? So then 0.5 mole H2PO4, 0.5 mole HPO4 2 minus would be the highest buffer capacity. Number 6, excuse me. Which of the following acids should be produce a buffer with a pH of 4.5? So in our lecture we talked about if you want to make a buffer of a certain pH, you should take the acid which has the pKa value close to the pH of the buffer system that you want to make. Okay, so we want to make a buffer with pH 4.5 and we are given Ka values. pH should be closer to the pKa of the acid that we're going to choose. Now all of these are given Ka and you guys know how to convert Ka to pKa. It's going to be negative log of Ka. So since there are 5 Ka values that we need to convert to pKa, instead we can convert 4.5 pH 4.5 into hydronium ion concentration and then compare that with the Ka values given. Okay, so again you guys know pH equals negative log of hydronium ions. So then the H3O plus would be 10 base 4.5, right? And that will give you the hydronium ion concentration, which is, let's try to do this one, log 4.5, 3.16 into 10 to the negative 5. So that's the hydronium ion concentration. So you find out of the acids given which one is the more closer to this hydronium ion concentration. Okay. You can, easy way that you can see is look at the exponent, negative 5. Find the one that is closest to that. That's going to be the buffer good to make a pH 4.5. Okay. All right. Excuse me. Number 7. A buffer is to be prepared by adding a solid sodium acetate 0.1 molar to 0.1 molar acetic acid. Which of the following concentrations of sodium acetate will produce the most effective buffer? Again, remember we talk about if you want to make an effective buffer, your acid component and the base component of the buffer need to be close to each other. So you choose the one that is closest to 0.1 molar. Out of these buffers, is it 2.5, 0.3, 3, 1.52? So choose the one which is closer to 0.1. Okay. Number 8, citric acid has an acid dissociation constant given. It would be most effective for preparation of a buffer with a pH of. Again, we are given the Ka. Like I mentioned before, if you want to make a buffer system, you would choose the acid which has the same or similar pKa as the pH of your desired amount. So here we are given Ka 8.4 into 10 to the negative 4. So we can find out the pKa of this acid using negative log of 8.4 into 10 to the negative 4. So find the pKa value. Okay, 8.4 into 10 to the negative 4. And find out which one is the more closer value for this given pH. Okay. find the pK, you guys can do that. And number 9, acetate buffer has a pH of 4.4. Which of the following changes will cause the pH to decrease? How do you decrease the pH? If the acidity increases, meaning pH lowers, right? So by adding a small amount of acid can decrease the pH. Okay, so adding a small amount of dilute hydrochloric acid, that's the correct answer. And then the next one, sodium hydroxide, when you add a base, it increases. Excuse me. Same thing if you dissolve, that's a sodium chloride. So sodium chloride is a salt. Nothing will happen if you add sodium chloride. And then sodium acetate also is not going to add any ions, hydrogen ions to the medium. So nothing will do. Dilute in the buffer solution with water. No. So the most effective way is by adding a small amount of dilute hydrochloric acid to decrease the pH. Okay. What will be the effect of adding 0.5 molar sodium hydroxide to an acetate buffer? Now earlier we had hydrochloric acid, now we are adding a sodium hydroxide. So what would happen if you add sodium hydroxide, which is a base? It will increase the pH slightly since it's a buffer. If it is not a buffer system, then it would increase significantly. So since it's a buffer system, this is given as your buffer. So it will increase slightly. Number 11, buffer solution with the component concentration shown below were prepared. Which of them should have the lowest pH? So for this one, you're going to be using our Henderson-Hasselbalch equation. Okay. In fact, you're going to be using that a whole lot to answer these questions. So your Henderson-Hasselbalch equation is pH equals pKa plus log base component of the buffer over the acid component of the buffer. First, you're going to get the B over A ratio, and then you're going to take the log of that. Okay. Now this is acetic acid. And we want to find out lowest pH. Okay, so pH, then I will do the first one for you. pH equals pKa. What is the pKa of acetic acid, which you can find if in an exam it will be given to you. So pKa of the acetic acid is 4.7. Since this is talking about acetic acid, we can use that, plus log base component is acetate 0.75. 0.75. Acid component also 0.75. 0.75 over 0.75 equals 1. Log 1 is therefore 0. So pH would be again 4.7. And if you take the next one, again 0.25, 0.25, that will also give you log 1 equals 0. pH would be 4.7. And same thing for this guy, 1, 1, same concentration, so the pH would be 4.7. But if you look at D and E, they have different buffer concentrations, 0.75 and 0.25. So when you calculate that, you put 0.25 here and then find out what's going to be the log term. And then if it is a positive value, you're going to add it to 4.7. Negative value, you subtract and find out which one gives you the lowest pH. Okay, that's how you would calculate that. Number 12. What is the pH of the buffer that contains 0.5 molar acetic acid and 0.35 molar sodium acetate? Again, we're going to be using this Henderson-Hasselbalch equation, which is pH equals pKa plus log base over acid. Okay, pH equals pKa. So Ka is given. So you can find out the pKa going to be negative log of 1.8 into 10 to the negative 5. So find out that pKa. Get that answer. Okay, pKa. And 1.8 into 10 to the negative 5. 4.74. Okay, so that would be 4.74 plus, no plus, 4.74 log, yes, there is a plus log base. What is the base component? Always the acid component. You have hydrogen intact, so the base you can find out either it is given as a negative charge species or as a salt like this sodium formate. So the base concentration is 0.2, so log 0.2 over 0.3. This will give you the pH of the solution. Okay, and once you find the pH, then you can find out the hydronium ion concentration. Okay, when you are calculating this, first take this number 0.2 over 0.3. That would be, we're looking at which one now? Are we looking at number 12? Got a little bit confused now. Okay, we're done with number 12. We're looking at number 13, right? Let me circle this one. So for the number 13, first do 0.3 over 0.2. What's the base concentration? Okay. We are looking at 12, right? Okay. I got a little confused. It's okay. Okay, 4.74, 1.8 into 10 to the negative 5. 4.74, that's correct. So we are looking at 12. Sorry about that. 4.74 plus log, and then the base concentration, sodium acetate 0.35 over 0.45. That's the acid, 0.45. So first get the 0.35 over 0.45, get that answer, and then you can take the log of that. Okay, and this would be point something like 777. Please check to see if my calculations are correct. Okay, and then take the log of that. That would be 0.109 negative. So 4.74 minus 0.109 will give you the pH of the buffer, and this is for number 12. Okay, all right. Okay, now we are looking at number 13. Number 13. Okay, what is the pH of the solution that consists of 0.5 molar ascorbic acid and 0.75 molar sodium ascorbate, and the ascorbic acid Ka given? Similar to 12, what do you need to do? You find the pKa, get the pKa, you know how to get the pKa, and put that value here, pKa that you're going to find. Okay, plus log, and then the base is 0.75 instead of 0.35. Now you will put base concentration 0.75 and then the acid 0.5. Okay, find the pKa, and then plus log 0.75 over 0.5. Okay, similar to number 12. Got it? Okay. And then the number 14. What is the... Okay, let me write down that so I will not get confused. 14. What is the hydronium ion in a buffer that consists of 0.3 molar formic acid and 0.2 molar sodium formate? And Ka is also given. Now, prior to we deducing the Henderson-Hasselbalch equation, so if you don't put it into your log terms, and I hope you remember, or you can refer to the notes again, lecture notes, hydronium concentration can be found by using this equation Ka times acidic component of the buffer over the base component of the buffer. And from this equation is what we come across, or we deduce the Henderson-Hasselbalch equation. So what we want to find out is the hydronium ion concentration. And we were given Ka. So then Ka is 1.7 into 10 to the negative 4 times acid component, formic acid 0.3 over base component 0.2. So this will give you hydronium ion concentration. Okay. That's number 14. Do your calculation and you will find an answer that you can see in the given choices. Number 15. Okay, we are looking at number 15. What is the pKa for the acid HA if a solution of 0.65 molar HA and 0.85 molar sodium acetate has a pH of 4.75? Again, you are using your Henderson-Hasselbalch equation. pH is 4.75, pKa plus log base concentration, this one, NaA, 0.85 over 0.65. So take 0.85 over 0.65, that would be 1.31, and then take the log of that, that would be 0.117. Do this calculation yourself and see if these numbers are correct. Plus 0.117, so you can find out the pKa would be 4.75 minus 0.117. That's how you would do 15. Okay. And 16. Number 16. Formic acid buffer containing 0.5 formic acid, 0.5 molar sodium formate. pH is given. What will the pH be after 0.1 molar sodium hydroxide has been added to 100 milliliter of the buffer? So we are adding 0.1 mole of sodium hydroxide to 1 mole of 1 milliliter, 100 milliliters of the buffer. So we want to find out the molarity of sodium hydroxide. So moles 0.010 and then the volume 0.1 liter. This will give us the molarity of sodium hydroxide that we are adding. There would be 0.1 molar sodium hydroxide. Okay, and then you are adding these 0.1 moles to your buffer solution, buffer system. Okay, so which component of the buffer is sodium hydroxide going to react? We are adding a base. So the buffer has formic acid and sodium formate. So which one sodium hydroxide going to react? It's going to react with the acidic component of the buffer, which is formic acid. So you write that equation HCOOH plus sodium hydroxide, giving you sodium formate plus water. and we're going to develop ice table for this. Initially, formic acid we have 0.5 and we are adding 0.1 molar sodium hydroxide, and sodium formate we have 0.5 and water doesn't matter, and the change 0.5, 0.1. So sodium hydroxide all going to react with formic acid. So change going to be 0.1. Sodium hydroxide all will react, and then a new amount of sodium formate that's going to form due to reaction of sodium hydroxide and formic acid going to be again 0.1, since 1:1 ratio. And then at the equilibrium what we're going to have is 0.5 minus 0.1 formic acid, because 0.1 has been reacted. So that would be 0.4. This will all be gone. So 0.5 made 0.1, so that will make it 0.6. Okay, now we found out what are the buffer components, base and the acid, after adding sodium hydroxide. Now you use these two to calculate your pH of the buffer using the Henderson-Hasselbalch equation. Remember the Henderson-Hasselbalch equation, pH equals pKa plus log base over log acid. And then the formic acid pKa is, what's the formic acid pKa? Okay, what would that be? 3.77. Yeah, Ka is 1.7 into 10 to the negative 4. pKa of the formic acid is 3.77. How do I find that? Remember in a previous question where we had formic acid in number 14, you see. So number 14, formic acid, Ka is given 1.7 into 10 to the negative 4. So when you calculate the pKa, which is going to be negative log of that, that would be 3.77. Okay, that's how I know pKa 3.77. So to find the pH equals 3.77 log the base. Now the base component is 0.6 and then the acid component is 0.4. Take the value 0.6 over 0.4, that would be 1.5, and then take log 1.4 and then you add it to 3.77. That will give you the pH. Okay. Alrighty, that's how you would do number 16. And number 17. A buffer is prepared by adding 300 milliliters of 2 molar sodium hydroxide to 500 milliliters of 2 molar acetic acid. What is the pH of this buffer? And the Ka is given. We done 16, now we are looking at 17. Okay. Again, buffer is prepared by adding 300 sodium hydroxide and acetic acid. So we're going to react acetic acid and sodium hydroxide. So CH3 COOH plus sodium hydroxide going to give you sodium acetate plus water. Okay, and we are adding 300 milliliters 2 molar sodium hydroxide, 300 milliliters 2 molar, and 500 milliliters of 2 molar acetic acid. What is the pH of this buffer? We need to find out from the given amounts what are the concentrations going to be when they are mixed with each other. So we can use M1V1 equals M2V2 to find out the new concentrations of our acid and the base when you mix together. So if M1 is 2 for acetic acid, volume 500 equals M2 is what we don't know what's going to be the new concentration, and the volume going to be 500 plus 300, 800. Okay, so then the M2 going to be 10 over 8. What? Let's see. Yeah, 10 over 8. 10 over 8. 1.25, right? 1.25 going to be the concentration of acetic acid. This would be 1.25 concentration of acetic acid. Similarly, you find the concentration of sodium hydroxide using the dilution equation. M1 for sodium hydroxide is 2, volume 300, new concentration we don't know, and the volume 300 plus 500, 800. Okay, so then the M2 going to be 6 over 8, which is going to be 0.75. 0.75. That's going to be sodium hydroxide. So we found the concentrations. Sodium hydroxide 0.75 and acetic acid 1.25. Now we're going to use those values to construct our ICE table. I just showed you how to get the concentrations. Now let's use those values. Initially, we have acetic acid now 1.25, sodium hydroxide 0.75, sodium acetate, we don't have anything yet, no water. Okay? And the change going to be sodium hydroxide, all 0.75 going to react with acetic acid. We're going to make then 0.75 sodium acetate. So at the equilibrium, it would be 1.25 minus 0.75. That would be 0.5. This would be 0 and this is 0.75. So when you mix these, it's asking what is the pH. Now you're going to use Henderson-Hasselbalch equation. pH equals pKa plus log base over log acid. So you want to find out the pKa from the Ka given. Right, you know how to get the pKa, negative log of 1.8 into 10 to the negative 5. So do this calculation and find out the pKa. Okay, convert it to pKa. So then your pH is going to be, after getting the pKa from 1.8 into 10 to the negative 5, you write down that answer here, pKa plus your log base concentration going to be 0.75 over 0.5. Okay, that will give you the pH of the solution and you will be able to get one of these answer choices. Okay, all right. Next one, number 18. pH of the blood is 7.35. It's composed of carbonic acid and bicarbonate. What is the ratio of carbonate to bicarbonate at this pH? Carbonic acid Ka1 given 4.2 into 10 to the negative 7. And again we can use Henderson-Hasselbalch equation. Find out the pKa. You know how to calculate pKa. pKa is going to be negative log of 4.2 into 10 to the negative 7. Okay, 10 to the negative 7. That's how you find the pKa. And then you use the ratio. What is the ratio? Okay, so when you do the calculation, you will be getting a pK something like 6.38. But make sure you do your calculation and find out the correct answer. Okay, I might be doing something wrong. So the pH is given as 7.35. Use Henderson-Hasselbalch equation. 7.35, pKa 6.38, and then you want to find out the ratio log carbonate bicarbonate, HCO3 minus over carbonate. ratio. This is what we want to find out. So 7.35 minus 6.38 would be 0.97 plus, sorry, not plus, equals log HCO3 minus over carbonate. How do you get this ratio? You take the log of anti-log of 0.97. Yes. To get the ratio HCO3 minus over carbonate, there would be 10 base 0.97. Okay. You will get an answer for that. That was number 18. Okay. Maybe we can stop here and I will explain the rest in the next one, probably. Okay, we'll stop here.